Hello again. I'm just going to try some problems where we use a bit of everything, the logarithmic rules, the exponential rules, product, quotient, and hopefully you get to see some variety and be ready for the test. I'm going to suggest the same thing that I told you before, that you should pause the video, try the problem yourself, and then take a look at how I solve it, and hopefully we have the same answers. And if not, just look at how I worked it out and find your mistake and try again. So here we have two functions. The first one, the log base 3 of sine x to the second, and I have rewritten both functions so that you can see, hopefully with the different colors, the different functions. So it's a function x squared nested inside the sine function, which is itself nested inside the log function. Same thing here, we have 5x to the fourth nested inside the ln, which is a power for 8. So I'll try the derivatives now. So for the first one, I have the log of an argument, and the rule says that my answer should be 1 over the argument, sine of x to the second. So I have to keep the entire argument, times 1 over ln of the base, which is 3, and then by the chain rule times the derivative of the argument, the derivative of sine of x squared. Well, the derivative of sine of an angle is cosine of the same angle, and then by the chain rule a second time times the derivative of the angle, the derivative of x squared, 2x. Now we can put it all together and have y prime equals, let's see, cosine x squared over sine x squared times 2x over the ln of 3. And you can see that we just multiply across. And then, of course, when you think about it some more, cosine over sine of the same angle, these two have the same angle, so we can combine them into just what's cosine over sine? Cotangent of that very same angle times 2x over ln 3. And sometimes, or many times, people write the coefficient first. 2 over ln 3 times x times cotangent of x squared. And there's your answer. But if you can have it, if you can have this expression, you will get full credit. Because we're just practicing the rule right now. Okay, let's try the second one. So we have the derivative of 8 raised to a power. I'm going to use the exponential rule. The exponential rule says I should keep the same thing. 8 raised to the ln 5x to the fourth, and then times, because my base is 8 and not e, I need a correction factor, so times the ln of 8, and then times the derivative of the power. The power is a logarithm function, or logarithmic function, so the derivative of that would be 1 over the argument, 5x to the fourth. And then by the chain rule a second time times the derivative of the argument, which is the derivative of 5x to the fourth, 20x cubed. And there you have it. This is totally okay. You can stop here for now, and I would grade it and give you full credit. But I'm hoping that you can notice that there's a few things you can simplify, like 20 divided by 5, x cubed over x to the fourth. Those seem simple enough. So we could have something like f prime of x equals, let's see, 8 to the ln 5x to the fourth times the ln of 8 times 20 divided by 5, 4, x cubed over x to the fourth. That leaves you with 1x in the denominator. So not that big of a difference, but this would be a better answer. So two more examples here, and I've tried the same thing. There's the outside function ln, nested, the log base 2, and 2x to the fifth. 2x to the fifth is the argument of log base 2, but then this whole thing is the argument for ln. And then here we have the product of 4 to the x times e to the 5x. So we'll try these. I'll start with number 3. So ln of a log, can you even have that? The ln of a log? Yes, you can. And so the rule says for ln, the answer should be 1 over the argument. And the argument happens to be log base 2 of 2x to the fifth. And then times the derivative of the argument. And what is the argument for ln? It is the entire log base 2 of 2x to the fifth. So the derivative of log base 2 would be 1 over 2x to the fifth. But then because it's not an ln, but a base 2, then we have to apply its correction factor. So times 1 over ln base 2, and then by the chain rule times the derivative of its argument. The argument is 2x to the fifth, and the derivative of that is 10x to the fourth. You follow this? First ln, 1 over the argument of ln times the derivative of the argument, which is 1 over the argument of that log times 1 over the ln of this 2, and then times the derivative of the last argument. Notice that ln did not need its correction factor. Like for log 2, we had to do 1 over ln 2. Here we didn't say times 1 over ln of the base, because when you think about it, the base here is e, and the correction factor would just be times 1 over ln e, but that is just a 1, so it's not needed. Make sure you spend a few more seconds looking at this and make sure you understand why this is the right answer. So now if we simplify it, we have dy dx equals, what can we do here? We have 10 over 2, that would be 5, x to the fourth over x to the fifth, so that's just 1x in the denominator, and then 1 over ln 2, and 1 over log base 2 of 2x to the fifth. And I think that's as far as we can take it. Now if you want to, you can just make it one fraction. 5 over x ln 2 times log base 2 2x to the fifth. And the entire time, notice that I didn't have parentheses around this argument, because it's understood to be the argument of log base 2, because it's what immediately follows log base 2. But if you think it helps, then go ahead and use parentheses on that. Equals dy dx. Now we move on to example 4, and we have a product. So we will try the product rule. And that one says the first times the derivative of the second, the derivative of e to a power, e to the same power, times the derivative of the power, and then plus the second, e to the 5x, times the derivative of the first, the derivative of 4 to the x, that is 4 to the x, times, correction factor because 4 is not e, times ln 4, and then if you want to, times the derivative of the power. But the power is just x, not a function of x, so it doesn't need a chain rule, but if you wanted to take it anyway, it'd be times 1. And that is the product rule. We use two exponentials. Notice the difference then. When the base is not e, and you take the derivative, you have to include that correction factor. When the base is e, and you take the derivative, you don't have to say times ln of e, because ln of e would just be 1. It does not need a correction factor, whereas the 4 needs it right there. So we can just rewrite it and say this is 4 to the x. Oh, that looks like 54. So let's make sure. Oh, let's make sure. Let's make sure that we don't say 54. E to the 5x plus ln 4 times 4 to the x times e to the 5x. That works. Again, if you just want to write the expression and not simplify it, I guess it's okay for now. I think I can do one more problem. So here's a quotient, and we have two exponentials, pi to a power, 5 to a power. None of those are e to a power, so they're going to require a correction factor. So let's get started. We have quotient rule. It starts with the bottom, pi to the x squared. Use parentheses anytime you do top bottom, times the derivative of the top, the derivative of 5 to a power, 5 to the same power, times correction factor because 5 is not e, times ln 5, times the derivative of the power, times 2. So let's see. Bottom times derivative of top, then minus the top, 5 to the 2x minus 6. If you want to, you can also have it in parentheses, it never hurts, times the derivative of the bottom, the derivative of pi to the x squared. Well, pi to the x squared would be pi to the x squared times correction factor because pi is not e, so times ln pi times the derivative of the power, the derivative of x squared, 2x. And don't forget, because you're going to lose half a point, not a quarter, but half a point, everything divided by the bottom, pi, pi to the x squared, squared. And I don't know about you, but I don't want to simplify that. So let's just leave it like this. That makes 14 minutes and 45 seconds. Goodbye.